So I got another request, a couple more. The first one is chapter 20, number 38. It says, estimate the volume of a hydrogen-filled balloon that will carry a 300 kilogram load in air. Assume the density of hydrogen is 0.09 kilograms per cubic meter, and the density of the surrounding air is 1.3 kilograms per cubic meter. Okay. 1.3 kilograms per cubic meter is the density of the air. Got it. 300 kilogram load being carried by a hydrogen-filled balloon with a density of 0.09 kilograms per cubic meter. That should be a slash there, should it not? Yes. Pardon me. There we go. And we've got this there. Mucho bettero. All right, I think I've got it set up now. So I like to draw a picture sometimes, it helps me visualize what's going on. So I'm probably gonna need to use most or all of this information. Sometimes they'll throw in extra stuff you don't need, but first thing I said is like, all right, I need to know the volume. Well, I have volume here. I have this many kilograms per that volume, but what I can do is just stick that over in an equation. Just put it there. I've got it, just put it there. And then I have these two. And you look at it for a second and you say, okay, air is 1.3 kilograms per cubic meter, but I need to displace enough of that air to float 300 kilograms of something, right? So I need to have enough hydrogen displacing enough air. How much air? 300 kilograms times the 1.3 kilograms per cubic meter that gets displaced. You follow? Where you got how much air do we have to displace to get enough weight displaced, weight of air? Remember, buoyancy, the buoyant force comes from the thing being displaced. So how much weight of air, not water, how much weight of air do we need to displace to get it to float? So 300 times 1.3 gives us 390 kilograms. That is the weight of the air that we need to push out of the way. And then it would push back, right? Newton's, what is it, third law, for every action force there's an equal and opposite reaction force. Good. So now it's easy. Once you get it in the formula, hopefully understand how I got it in the formula. Because now all we have to do is divide it out, okay? So again, we need to displace this much air, and we have kilograms over here and kilograms over here. We're looking for how much volume of that hydrogen we need to displace. So we're gonna say, divide out the kilograms, right? So that gets rid of that. All we're left with on this side of the equation now is our cubic meters, and that's going to be equal to 390 divided by 0.09 kilograms. The kilograms go away, which is good because we're not looking for kilograms, we're looking for our volume. And we do the math, and I had it written here for me, so I didn't have to remember. We get 4,333.3 repeating cubic meters. That much hydrogen. And if we want, we can say, well, how much weight in hydrogen is there? So I can, if I wanted to, I could take that number. Let me get my calculator. So 33.3 times the weight, 0.09, for each of these cubic meters is 0.09 kilograms, right? Hit enter, and I get back, lo and behold, it makes sense now. I get back to 300, it's just rounding error here, right? 389.997. It's 390 kilograms. So the weight of the hydrogen, which really doesn't matter, but it should be equal to the weight of air it displaces. Does that make sense? If it's less than that, it's not just going to float, it's going to continue to go up. If it's more than that, it'll start to sink. Hopefully that helps. If not, we can discuss further. Let's get this out of the way. Yeah, why did I put that again, right? Cubic meters equals such and such amount of cubic meters. I mean, it's not wrong. Anyway. Next question. See if I've got that in the spot I want it. Next question, I think, was number 40, because we did number 39 together already. So chapter 20, number 40, estimate the ratio of the atmospheric buoyant force per unit of body weight for an average person. Oh my heavens. I hope they gave us maybe, oh gosh, it just dropped that down. I'll just drop that down too. Okay. I hope it gave us somewhere in the chapter the density, what was it we were looking for? The buoyant force per unit of body weight for an average person. So let's look and see if we're given that. Admittedly, when I read that, I'm like, somewhere in the passage it must say, and I looked what the average body weight for a average person is, and I couldn't find it. I'm like, I'm overthinking it. How many of you overthought this one? So go back to the one we just explained, number 38, and I explained how it should be the same. The helium, the mass of all of the helium, or was it hydrogen? It was hydrogen, that's floating that weight would be the same as, or approximately the same, otherwise it'd go up or down, right? As the amount of force, mass that it's displacing, because that mass is going to create the buoyant force. So it should be close to 1-to-1. That's it. Is it like, it's almost a trick question. It just makes you think a little bit like, okay, average person's weight. That's not the weight, but it's a ratio compared to the buoyant force. Okay, so if I'm dropped into water or atmosphere, whatever it is, if a person is put in some sort of a fluid, they're going to displace enough of whatever it is that it would push back with an equal amount of force to their mass. Does that make sense? So it's almost a trick question. It's just 1-to-1, yeah, like the last example. Anyway, I think that's enough said, I think. If not, let me know. And then we have number 42. Asks, how many newtons of lift are exerted on the wings of an airplane that has a total area of 100 square meters when the difference of air pressure below and above the wings is 5% of atmospheric pressure? Now, if you go dig back in the chapter, it says pressure difference times wing area gives you lift. Does that make sense? Okay, so it's how much or how many newtons of lift. We want this lift in newtons. All right. Where do I start? So I draw a picture, right? I've got my wing. We know that there is air going over and under. The air going over has to go faster. Bernoulli's principle states that a fluid moving faster will have a lower pressure. Fluid moving slower will have a higher pressure. Okay, cool. So we're going to have a difference in pressure. They give us, it's a 5% difference in pressure from above and below. If we assume sea level pressures, okay, let's say the airplane is not flying, at 50,000 feet. We've got 100 kilopascals of pressure for the air, which is also equal to 100,000 newtons per square meter. Okay, that's just info out of the book. And we can multiply that then, 100 kilopascals times 0.05 will give us our 5% difference. So we're to 5 kilopascals, or we could represent that as 5,000 newtons per square meter. We're given the number of square meters the area of the wing is 100 square meters. So we can take our 5 kilopascals, or 5,000 newtons per square meter, times 100 square meters, and we're going to end up with just adding a couple zeros, right? So it'll be 5 and 1, 2, 3 plus 2 more zeros. We've got 500,000 newtons of lift, if that makes sense. Now we could go a step further if we wanted to and say, okay, how much weight is that? Then you would just take your 500,000 newtons to find out how much weight that wing could lift. Of course, that would have to include the weight of the wing, but we'd take the 500,000 newtons divided by 9.8 meters per second squared, because that's acceleration due to gravity near Earth's surface, and a newton is equal to kilogram meters per second squared, right? So we can divide out the meters per second squared, because this is a kilogram meter per second squared. We'd get rid of the meters per second squared and be left with just kilograms. So what is 500, 1, 2, 3 for 1,000, 500,000 divided by 9.8 gives me 51,020. 51,200 or 51,020? 51,020 kilograms. Apologize for the phone call. Good grief. So this wing can lift, in this scenario, it can lift 51,020 kilograms. Now that includes the wing itself, but and of course, to make it make more sense to us, we could convert that back to pounds. What is it to be divided by? Is it 2.2? I always forget. I think, or is it times 2.2? She won't give up, will she? She's. So we're going to say times 2.2, and that gives us 112,000. That seems like a lot. That doesn't seem right. Let me check my math here. The difference between the low and the high pressure is 5% of the atmosphere, the atmospheric pressure. Atmospheric pressure, 100 kilopascals. So to get 5% of 100 kilopascals, we just multiply it by 0.05. So we get 5 kilopascals, or we could represent that as 5,000 newtons per square meter, because that's what kilopascals are. They're newtons per square meter. Okay. And then we're going to multiply that by 100. Why are we multiplying that by 100? Well, because we have 100 square meters. So that many newtons per square meter, and we have 100 of them, so we get 500,000 newtons. A newton is a kilogram meter per second squared. So if we divide that by the force of gravity near Earth's surface, not the force of gravity, the acceleration due to gravity, which is 9.8 meters per second squared, we divide it out, we get a number right here, 51,020 kilograms, times 2.2 gets you just over 112,000 pounds of lift, okay? A 747 jumbo jet, I looked up, has about just over half of this wing area and can lift hundreds of thousands of pounds. So this is not unrealistic at all. If you have any questions, let me know.